Hello everyone, this is Dr. A, and this part relates to lab activity 6. And here I'm going to talk about curve fitting and interpolation. So what you probably watched in the videos related to this week, you got familiar with the Excel tools and some functions we have, and these are included as trend line, slope, intercept, RSQ, linearest and longest, and regression tools. And you also saw that R squared used in order to determine the goodness of fitting of a line or a curve to the raw data that we have. And the R square has a value between 0 to 1, and when it gets closer to 1, that means we have a better fit of our data. And this is useful when you are comparing different models that may have a different number of parameters. Okay. Now, I want to bring a practical example of how we are using this fitting in research. This is related to calibration of a pneumatic valve. So basically, what we have in this system setup is two containers, as you can see here. And in these two containers, they are packed with um, hitting packages that they can, if you want to hit them up, then you can do that. And it's a really simple system as water comes in, going through two pneumatic valves, and then each of these water lines will go to one tank, and then these two tanks are connected to a third tank, and they are actually uh, uh, disposing what they have as water into the third tank. So basically, if I want to show it in another uh, perspective, this is with the lab view. You can see that water comes here going through a pneumatic valve. It may get hit up with the package that it has around it. Water also comes and go through another pneumatic valves, comes here, and then they all get into another line so that to get to the third tank. Okay, so it is just a mixing process of two tanks. So very easy physical setup and physical process without any reaction. Okay, and what we want to do is to calibrate the pneumatic valve we have here. Okay, we can just pick one and calibrate one of these two pneumatic valves. So when we do that, based on the percentage of openness of this valve, we have an amount of water going through that, and we can measure it with this manometer in gallon per meter or liter per minute. So basically, what we have eventually as our data is valve openness, like when it is 20% open, this valve here, then the flow rate will be zero point 0.4 liter per minute. And if we gather some data, then we can come up with the calibration curve. So eventually, this is going to be our data points, these red bullet points that you can see. And then you can fit different types of equations with their corresponding R squared values. So here you can see that I'm fitted these raw data related to the calibration with the polynomial power of 6, polynomial power of 2, and then a linear equation. So three forms of that. So for the first case, the R square is 1. For the second case, the R square is 98.98. And for the third case, it is 0.97. Okay. So now if I ask you which one is the correct fitness line or fitting line for this raw data, then maybe if you just put your focus on the value of your R square, how that value is closer to 1, then maybe you pick up the first fitting and you say that, okay, this one is the best fitting line. So from the mathematics aspects, that is right. But from the physical aspect of the system, we cannot justify what these parameters are here that we have in the equation. Okay. So basically, if you want to be accurate and consider the physical aspects of your system, you have to fit this raw data you have for your system with a linear equation. That means y equal to ax plus b. Okay, so this is actually the right format, the correct format of fitting, regardless of what value r squared could have. So for real systems that we have in engineering, you need to consider both mathematics and physical aspects of the system. So this is going to be the right fitting, but still, when you look at this fitting, this is not completely right. Why? Because if I give as a value of 0, then I will get a negative value for y. X, if x has a 0 value, that means the valve openness is 0. And when the valve openness is 0, that means the valve is completely closed. So when the valve is completely closed, then we do not have any flow rate. So y must be 0. So you can see that the system dictates what type of equation we can actually fit to the raw data. So if we want to be accurate, none of these equations we have here are correct to fit to this data we have. And basically, this is going to be the right one where we can see when x is 0, y is 0. So when the valve openness is 0, the flow rate is 0. So this is going to be the right format of how fitting a line to the raw data we have, and it must be linear. And if you note, for all the measurement tools we have, and when we want to come up with their calibration curves, we always want them to be in the linear form. Okay. Now, so based on the raw data we gather, here I want to show you another example of that. And this is related to estimate the rate when x has a specific value. So, but we don't want to get too deep in the data we have here. Finally, what we have is the rate versus the mass composition of a system, and we have these raw data points, as you can see, and they are all over the place and they are really scattered. When you look at it in the graph, they are really scattered. And if you want to fit it, you could fit it with different forms and with different, you know, lines. So one way of fitting is that to consider some of the points and then neglect some of the other points and then come up with like this dashed curve line, or you can come up with this bold blue line where we are considering some other data points and then we actually neglecting these data points. So basically, in these cases, when the data points are really scattered, you can ignore some of the data points which are very maybe far from the others, and then come up with the fitting, and then you can actually come up with the equation as well as the r square. Another way of that is to do a linear interpolation, which means going 2 points by 2 points and then start connecting all these lines and then say that, okay, I have these lines, and then I will come up with the equations related to these lines in order to explain or to describe how my data points are changing, which is a tedious work to do. And in this case, again, it is better to go with the this curve with the as a polynomial second order with this equation to describe the data points. The other way is a Lagrange polynomial. So this, if you go with the with the order of two, you may come up with this dashed line here. And as you increase the order of your polynomial, you're getting closer and closer to these data points here. Okay. And then you can come up with a better estimation. But again, you need to note that as I showed in the calibration example, you cannot just go as far as like 20 or 30th order of polynomial, because if that data is related to an engineering system, then you need to justify the terms that you are adding on the right side of your equation. Okay. So basically, in this case, if we really don't want to go to really high values of uh, order of polynomial, the best bet would be just to go with the polynomial of order of 2, uh, even when the R square is not really high, it is just zero point 0.7. Okay. Now, let's look at a different data set here. And this is related to like saturated propane temperature, changing with the temperature. So this is like heat of vaporization versus the temperature. And usually you will see in thermodynamics, in transport, all the graphs that we have like such type of data. What I mean is we have many data, and the data are not scattered like the previous example. And this actually helps us to understand our system much better. Okay. Like here, this is the heat of vaporization, and you have many data that are really close to each other, and they can easily form a curve here for you, so you can really understand how the system is working and how the parameter is changing. So here, if you want to do any interpolation, you can easily do that by fitting even a linear line, because up to here, from here up to here, you can say that you have a linear system, and then it gets away from the linearity, and then you have some, some curve or some changes that are not linear. But depending on where you want to do interpolation, you can easily do interpolation from this range up to here, this range. So these data that we have, uh, like such, you can see one of the examples here. You can easily do interpolation. Like here, you can estimate the specific volume of propane at a specific pressure and temperature. So you can easily use the data you have, and these data are too many data points. So you should be good and safe in order to do interpolations here. Okay. Now, for today's activity, we are looking at the reaction rate of Alka-Seltzer in water. So if you put Alka-Seltzer in water, it starts, bubbling, and then you will see that it's gonna spread in water, and then you will see that the mass of the tablet will go down. So in this activity, we have a small portion of water which we already measured, and it's set 175.82 gram. Then we also have a mass of Alka-Seltzer tablet, and it has a mass of 3.04 gram. We put the cup of water on the scale, and then uh, we record the decrease of the mass, and we gather the data by using a stopwatch as we drop the Alka-Seltzer tablet into the water. The data was recorded for the total mass of the tablet every 3 seconds for 5 minutes. And I'm sharing with you the Excel file where you have access to this data, and that Excel file is entitled Lab 6 data. Now, what I want you to do is based on this data set, this Excel file. So first thing that you need to do is to generate a graph of mass versus time and find the best curve fit of this data. And the second thing that you need to do is to use this curve fit to estimate the mass of carbon monoxide emitted at 30 seconds and at 2 minutes. And in the last part, you need to explain whether your curve fit does better or worse than what you expect. Okay? All right. With that, we are done with lab 6. Have a good day. Goodbye.